Good evening and welcome to this first video of this tutorial session on electrical machines 1. This is the week 0 assignment discussion on the fundamental concepts about electrical machines. I am Saptarshi De, a PhD scholar at the Department of Electrical Engineering at IIT Bombay. Here we will discuss mostly 9 questions from question numbers 12 to 20 of week 0 assignment. All the questions are based on Lorentz force. This is a Lorentz force expression which gives the force on a conductor, force on a moving charge in a magnetic field B, which is given by F equals Q into V cross B. V is the velocity, B is the magnetic field intensity, F is the force. Now the first question says that a straight conductor of length 2 meter moves with a velocity of certain velocity and in a magnetic field of certain magnitude. Where will be the direction of EMF in the conductor? So we can see here that V is in this direction while B is in this direction. So we have to do a cross product between these two vectors V and B. So we will simply apply a right hand screw rule which will be like this, and hence we will get the EMF from X to Y. So basically what is happening is that if I consider a positively charged particle inside the conductor, it is experiencing a force along my thumb. So it will try to move from X to Y. Hence the EMF will be, the EMF will be in this direction. So here the option A will be correct. Now in this question the same setup is there, and now the value of EMF has been asked. So we have to now find out from this expression how much is the force on one positively charged particle of charge Q. Now we can see here that the direction of velocity of this conductor and the magnetic field, they are perpendicular to each other. So we have QVB sine 90, sine 90 is 1, so we have QVB. This is the magnitude of the force acting on one charged particle of charge Q. Now this force is moving this charge along this conductor is of length, let us say length L. So dl is the infinitesimal length along the conductor. Now work done by this force to move this charge for an infinitesimal length dl is given by this expression, integration over f dot dl, and we get QVBL. So this is the work done by this field to move one charge from one end to the other. And we know that EMF is work done per unit charge, hence EMF is BLV. Now substituting the values of B, which is 0.8 Tesla, L which is 2 meter, and V which is 5 meter per second, I get EMF induced in between these two terminals X and Y as 8 volt. Moving on, the same setup here, the only difference between the direction of velocity has changed. Now the velocity is parallel to the magnetic field B. So the angle between them now is 0 degree. So we are applying the same equation, we get QVB sine 0. Hence in such a case there will be no force acting on this conductor. So when a conductor is moving, sorry, no force acting on the, not the conductor, no force acting on the particles. So in this case there will not be any EMF generated between these two terminals, since the conductor is moving parallel to the magnetic field. Now again the same setup, but in this case the direction of velocity is 30 degree with B. The question is same as question number 13. Only thing is here it is being sine 30 as the angle between these two vectors is 30 degree. Sine 30 degree is half. So we have force as half of QVB, and then proceeding the same way we have work done as force times unit length and EMF as work done per unit charge. So we get half of BLV, half of what we get last time, and thus we get the EMF between these two terminals X and Y here as 4 volt. So what we got is when the conductor was moving exactly perpendicular to this magnetic field, the EMF between X and Y was highest. While it was moving parallel to the field, the EMF between these two terminals was lowest. In between, it keeps on decreasing. It keeps on decreasing like this. So if I draw a sine wave, this is the 90 degree and this is 0 degree. It keeps decreasing in this fashion. Now we can say that the problems that we have considered till now are all generating problems. There was motion, EMF was being generated. Now it is the opposite. There is current, and we will try to find out in what direction, in what direction the force will be generated. So this is motoring. Now here we can see that there is one EMF source, there's a voltage source here which is driving a current through this conductor and conductor is placed in this magnetic field B. So the current flowing in this conductor is like this. So let us assume a positively charged particle in this conductor at this place. Okay. So this, since the current is in this direction, the positively charged particle is moving in this direction. Again, we will apply the same Lorentz force here. So direction of, if I draw it here, this is the direction of V, velocity, and this is the direction of B, magnetic field. Now if I do V cross B, which is again the right hand screw rule, I will put my hand along V, then curl, and I will get, my thumb will be upward, so the force will be in this direction. So this conductor will experience a force towards upwards. So in this case, we will this conductor, when current carrying conductor when kept in this magnetic field, will experience a force in this direction. Now the same setup, we have been asked to find the value of the force. There are formulae here, but I would like to use as less as possible. Only thing we will use is this Lorentz force formula, which is Q into V cross. But before that, we will look at what is given to us. We have been given the length of this conductor, the current, and the magnetic field intensity. Okay. So what is current? Current is rate of change of charge, rate of flow of charge, dq dt. Now, using the chain rule of differentiation, I can write this as dq dv into dv dt, where dv is one infinitesimal volume on the conductor, which looks like this. dv is infinitesimal volume of the conductor, and the area of cross section is same, and this length is an infinitesimal length dx. All right. So dq dv actually gives me the amount of positively charged particles in unit volume of the conductor. Now obviously this thing depends on the material, and this will remain constant because we know that when current flows through a conductor, the conductor remains neutral. So the total number of positively charged particles or protons or electrons, if you can say, they remain the same. Only thing is they flow. So dq dv will remain constant, and dv we can write as from here in this diagram you can see that dv we can write as a dx. So I am substituting dv as a dx, and final, and dx dt is nothing but velocity of this particle. Since x is this direction, so dx dt is velocity of the particle, charged particle. So I have current expressed as this: area of conductor velocity of charged particle and charge density in the material. So you can see that current is proportional to the velocity of the particles. Higher the current, faster they move. A and dq dv we can assume constant for a given size and material of conductor. Alright, so we have expression for current. Now we will see what is the force. Now we have seen that force on one charged particle of charge q is given by q into v cross b. Okay, this is given by q into v cross b. Now there are n number of such charges, and the total force on this all the n number of charges is the total force on the conductor. I do not know how many charges are there, so I have multiplied with n. So this nq v cross b is the total force on the conductor. Here the velocity of charged particle is in this direction and b is this direction, so they are perpendicular to each other, hence we have sine 90 degrees, so we have nq vb. Okay, now what is nq? Nq is the total charge present in this conductor. So this nq we can write as volume of this conductor, which is Al times its charge density dq dv. So I have substituted nq as this Al dq dv. Again we have a times dq dv times v as current from this equation. So substituting, I get the force to be equal to BIL. Now we can simply substitute these values and get the force as 5 into 2 into 0.8, which is 8 Newton on this conductor, and the force will be upward. We have seen in the last problem. Alright, now it's a bit more complicated, but nothing has changed. The principles are still the same. This is what actually happens inside a machine. You have a field, you have a loop or a coil carrying current, and uh, there is some force on it. So basically, see what is there. I have the field, I have the current, and I have been asked to find out the force on the conductor. So this is a motoring action. This is very important to understand which is the cause and which one is the effect. Here I have been given the field, I have been given the current, I have been asked to find out whether it will rotate or not. So basically I have been asked to find out the torque. So this is the motoring action. Alright. So again, let us consider a charged particle here. So it is moving in this direction. So V is in this direction, B is in this direction, and if I curl my hand like V and I push it towards V and then curl toward B, I get a downward force on this conductor. So this conductor will experience a downward force. So let us assume the axis of rotation something like this. Okay. Similarly, the direction of V here will be like this, while B is the same. So I have again right hand screw rule, the force to be upward. And if I consider the force here, the V and B, they are parallel to each other. So there is no force acting on this part of the conductor. So only these two arms, again similarly no force acting on these two parts. So these two arms are getting forces. How are they getting? If I look at them like this, so this is the conductor on my left side, which is carrying a going current, and this is the coming current. So I have downward force on the left hand side conductor, upward force on the right hand side conductor, hence a moment like this is creating. So from here I will see a counterclockwise rotation of this system. So this whole loop, this winding or coil, this coil will try to rotate in counterclockwise direction. Now the same setup, only thing is uh, its direction has been moved, the alignment of the coil has been moved, and again we have been asked to find out whether the coil will try to rotate or not. So now here we have similarly V in this direction and B in this direction. So again the right hand screw rule, we have force towards up. Now again the axis of rotation is this. So here we have upward force. Similarly, I have V in this direction, B in this. So a downward force acting on this arm on the conductor. And again, in this arm, I have V here and B here. So outward force, force along the axis outwards on this arm. So basically, we can see that what is happening if I see this is the upper conductor carrying a coming current. This is a lower conductor carrying a going current. This is the axis of rotation. But it is experiencing a force towards up. It is experiencing a force towards down. Whereas, so from here we can see that they're cancelling each other. So net moment is zero. So in this condition, what is happening is the coil, which actually let us say looks something like this, it is trying to bulge out. I am exaggerating obviously. This coil, due to this force, is trying to bulge out like this, but is not definitely trying to rotate. There is no force to rotate it. So what happens in motoring mode is when the coil is in this fashion, it is getting the maximum amount of torque and it is accelerating, and that and it is rotating in some fashion. In this fashion it is rotating. Okay, the torque on this conductor keeps on dropping, but the torque is still is in this direction, so it is accelerating. Acceleration is reducing, and once it reaches here, the torque on it is zero, but it skips this position due to inertia, and once again the torque keeps on increasing. It gets the maximum torque while reaching this position once again, and this way the torque is continuously acting on the conductor. So till now we have talked about motoring. Why do I say we have talked about motoring? Because we have been given the field, we have been given the current, and we have been asked to find out the direction of motion. While in generating, this is a case of generating. While in generating, we have the opposite. In generating, we have the field present. We have the motion present, right? A generator is run by some prime mover from outside, and we have been asked to find out the EMF. The load of a generator is some electrical load. This here in this case the resistance. So this is a generating condition. The approach will change because in this case um, the causes have changed, and we have been asked to find out the effect. Okay, but this fundamental equation, this never changes. This is applicable everywhere. Okay, so let us for the time being suppose that there is no current in this conductor and it is being rotated by some prime mover. So there is one charged particle here. Okay, and its direction of motion is downward. Now, see, this direction of motion is not the current. This particle was residing in the conductor. The conductor is moving downwards, so the charged particle is moving with the conductor downwards. Right? It is moving downward because the conductor is moving downward. Okay, and B is in this direction. Right? So now if I apply this right hand screw rule, it is coming out that mm, oh, sorry, I drew the velocity opposite. It has been given that it is moving in this fashion. So since this conductor is going up, see, this is going up, so the velocity is in this direction. The explanation was not wrong, the drawing was wrong. And the B is in this direction, so I have the force on this conductor in this direction. This force on this conductor will create the current to flow in this circuit. We can verify it here also. This conductor is, as you can see, going down, so a charged particle, positively charged particle, is going down with some velocity v, and B is in this direction, so the force acting on this is in this direction. So what we have is, if I clean out these things and only draw the force, so the force was in this direction here and in this direction here. So a current will be flowing like this. So let us find out which one are correct here. So A B C D E F, current is flowing in A B C D E F. And what will happen? See, this current is flowing like this through the resistor, so it is creating a voltage drop. So this will be plus, this will be minus, right? So this F terminal will be plus, A terminal will be minus. So F is positive, A is negative. This is the correct answer. And will there be anything else? Okay, current will be flowing from FGHA. FGHA, this one, this will be correct. So I have covered all the questions given in week 0 assignment, which were based on Lorentz force. So the bottom line is, whatever might happen, whether it is generating, whether it is motoring, it does not matter. This formula, this basic formula, F equals Q into V cross B, this thing always holds. Even if you forget Fleming's left hand rule, right hand rule, it does not matter. Simply apply this F equals Q into V cross B rule. If you see closely, Fleming's left hand rule is nothing but a cross product. This is the current, this is the magnetic field, and you get the direction of movement. Fleming's left hand rule is nothing but a cross product. So this formula always holds. You need not remember which one is motoring, which one is generating. Just use this formula and remember the cause and the effect. Okay, we will meet in the next class. Thank you.